Thanks, thanks to the organizers for this workshop. It's super fun. So this talk is going to basically be an overview of a line of work many of us have been involved with in how we estimate certain latent variable models and how basically tensors have arisen in certain statistical machine learning problems and statistical estimation problems in a very natural way. And two of the problems we're going to highlight are this mixture of Gaussians problem, where you see a bunch of points like this, and you would like to figure out the means of each cluster. This is a classic statistical problem. The kind of discrete analog of this problem is a topic modeling problem, where you have collections of documents, and you'd like to estimate the topics in these documents. Most of this talk is going to be reviewing things I've spoken about before, but I'll highlight some work on a recent result looking at HMM. So an interesting question for modeling discrete time series. Suppose you have something like, a DNA sequence. So on. Okay, so you observe the sequence, and it's natural to posit that there's some hidden structure in this. And the way the sequence is generated is based on some memory. So the state, there's a state here that's transitioning, and that encodes the information. And you see these sequences, and you'd like to build a model of this hidden structure. And what's interesting about this problem that's pretty different from these is these we think of as kind of high-dimensional observations. Okay, this one's low, but typically when we're clustering, our points live in a high-dimensional space. When we're dealing with words, the number of words in the English language is like 10 to the 4. Whereas here, our observations are rather low-dimensional. There's 4 discrete objects. So I'll highlight some results here, but it's kind of a different problem, the challenges we face in this setting. So what's our goal here? We see data. We'd like to estimate this hidden structure both efficiently from a statistical point of view and a computational point of view. Right? And what's used in practice? Well, these really are long-standing problems. And often what we use in practice are iterative methods like k-means, EM, Gibbs sampling. And we don't have a very good understanding of their convergence properties.
So by statistical efficiency, you mean the number of samples? The
number of samples, that's right. There's sort of even information efficiency we'll discuss, which is like notions of window size, like how long of sequences do I need to keep around for this HMM problem. Okay, so in terms of lower bounds, we know this mixture of Gaussians problem in the worst case can be hard because you can have these examples that, basically you can make one Gaussian look like, this is a very nice example by Greg and Encore. You can kind of make one Gaussian look like a mixture of a few of them that are reasonably well separated, basically just like by the convolution theorem. You're going to have to kind of futz with the tails a bit, but somehow you can make a mixture of, you can basically make, one Gaussian look like a mixture of k Gaussians. And these are reasonably well separated. And the point is, if I give you an example like this and ask you which one it is, these should be flat. But just think, a Gaussian is a convolution of a bunch of other Gaussians. You can futz around with it and get it to work out. And the point is, this sort of problem, they're reasonably well separated. They'll be Pauli in K, where K is the number of Gaussians. But the number of samples you're going to need to distinguish these two is going to be exponential in K. Okay? And this is a hard case because these parameters in parameter space are super far apart. Right? It's not like, certainly as some Gaussians get close together, it's going to be hard. But this is a very different problem. These parameters are nowhere near each other, yet you can't distinguish them. So we know this case has to be hard. But what's interesting about this HMM problem is it's a very different hard case that we know of. Okay, so this is, we can really think of a statistical lower bound. For HMMs, there's this sort of this classic problem in CS theory in learning theory called parity with noise. So this is, so let's forget about noise. Suppose we have, a set of zeros and ones. So we have a vector x1 to xn. This is binary. And you're going to see some target y, and it's just going to be the sum of, let's just say, a very small number of variables, but it's going to be some mod 2. Right? So 0 plus 1 will be 0, and so on. Okay? And if there is no noise in this, so basically there's maybe 5, a small number of them that are relevant. You see examples. There's just some arbitrary distribution over x's. But if there's no noise in this system, you see a bunch of examples, and you'd like to learn these relevant variables. This is an easy problem because it's Gaussian elimination. You're just solving a linear system. Right? And the parity with noise problem is, now you see 0, 1, 1, and it should be 0, but someone's adding a little noise to the problem. Right? And it's clear Gaussian elimination is a disaster now. Right? And this is really a tricky problem because we have no idea how to solve this. But it's an interesting one because statistically, there's no problem. Like if we didn't have computational resources, this is an easy problem. So it's really a good hard case. It's not like these NP hard problems. It's the kind of thing that crypto people build primitives of, because how the heck, we just have no idea how to solve it. And what's interesting about this hard case, the main point I'm bringing it up, is you can embed these hard cases in HMMs. That basically what you're seeing is some zeros and ones for a while, and then after a while you see a parity at some time step that's corrupted with noise. And this sort of suggests that computationally, we should not expect to learn general HMMs, and kind of for different reasons than this lower bound for the Gaussian mixture model, because it's sort of worse in a lot of ways, because statistically, this is an HMM that we know is learnable with a small number of samples, but it's really, there should be no way around this HMM. So it's interesting to consider what are the cases which makes problems hard. And to some extent, the highlight of this talk is under certain assumptions that are pretty natural, we can get around these hard cases. In a number of interesting practical cases, we basically have nice closed-form solutions of estimating these model parameters through the use of certain tensor decompositions. And to some extent, what's going on in these problems, you just need a little genericness to your problem to break these hard cases. But it's sort of different in each case. And this talk I really focus on 2 of these simple problems, which are this topic model problem and a very simple version of this Gaussian mixture problem. I'll highlight some of these results for HMMs. And in the next talk, Arang is going to really give highlight some very nice recent work on learning this general Gaussian mixture problem, because it's a very different sort of tensor. It's a tensor made of PSD matrices. So this talk is really just going to go pretty slowly, going through some base cases of how we look at tensors, how these tensors arise in some basic models in machine learning. And it's suffice to say there's really been a lot of work on the statistics and computer science community on these problems. Like the Gaussian mixture problem is a classic problem dating back to Pearson. I would say this line of work for us, similar tensors have arisen in different areas for different reasons. And this line of work really, I think for me, traces back to Joseph Chang, a statistician at Yale now, where he really understood some of these identifiability issues for phylogeny trees. That sort of evolved into Elhanan's work and others. But there's been basically different lines of work that we can trace this back to. Okay, so set up the problem for the question of topic models and mixture of Gaussians. Definitely ask questions if things aren't clear. But we'll set up these 2 cases. I'll highlight what's going on in these time series models like HMMs along the way. And we'll just look at the structure of this problem and see how it's related to tensors and the types of decompositions we understand. OK, so let's look at a simple version of the Gaussian mixture problem. The parameters are means, which are denoted by mu1 to mu k. Let's generate our data. OK, so how are we going to do it? For each data point, we're going to sample a cluster I with probability wi. And the point we observe is just going to be this mean mu I plus some noise we're adding to it. And let's say the noise is spherical for now. It might have different variances. So Rang's going to look at the general case later on. So basically, that picture I showed you is we're just getting samples of these means corrupted with noise. And then your job is like, here's your data. Tell me the parameters in the model. That's how I'm going to phrase it for you. So you just see a bunch of points, and I'd like you to tell me the mu's, the w's, and the sigmas. And let me give you this question for the topic model, the topic modeling problem, which is, you can think of this as the discrete analog of a mixture of Gaussians problem, but there's some differences. So in the topic model problem, instead of means, we have multivariate distributions, mu1 to mu k. Multinomial distributions, mu1 to mu k. And what we do now is first sample a topic I with probability wi. So a topic might be sports, and the sports topic just specifies a distribution over words related to sports. Where we generate our document now is we're going to take m draws from this particular multinomial distribution. So if we choose a history topic, we're just going to generate independently m words related to history under this topic. And then what you see are collections of documents. Ignore the order in the words. And you'd like to figure out what are sports topics and history topics and so on, where the sports topic is a distribution over words. And in this HMM model, you can think of this as just a generalization of the topic model. Whereas the topic model, in a sense, you can think of this hidden state as being fixed throughout the chain. Okay, whereas in HMM, the first word could be generated according to one hidden state, then there's a transition, there's a different hidden state. So in a sense, these topic models are a degenerate version of HMMs, where this transition model is the identity. Okay. And again, the HMM is you see these sequences, you'd like to learn the hidden structure.
HMM like models also being used for topic?
Sometimes.
Imagine the topic evolves as the document proceeds.
Yeah, so often they capture shorter term timescales. Typically, this is the harder question is how do we do these things hierarchically, where HMMs tend to work better for like part of speech structure because that's sort of faster changing things. And when you run them in practice, they occasionally pick up topic stuff, but they're much better at picking up kind of the part of speech structure in sentences.
Sorry, maybe you said that. Do you know K?
Sorry?
Do you know K?
Let's assume we know K for now. Yes, let's assume we know K for now. I mean, at some level, you can search if you have a polytime algorithm, but right, this is not. Okay, so what's the game we're going to play? We're just going to look at, instead of maximum likelihood, let's just go back to this old idea from Pearson, which is the method of moments. And it's a simple idea. Look at correlations in your data. What are the parameters consistent with the correlations you observe? Right, this is sometimes referred to, this is the inverse moments problem. It's kind of studied a lot in mathematics. And it's pretty intuitive. So the mixture of Gaussians problem is what are the moments, where the first moment is the mean of your data, the second moment is the covariance matrix, the third moment just specifies the three-way correlations. For the topic model, these moments are interesting because what is the first moment of your data? Well, you can think of this as just specifying the distribution over a single word. You can think of the second moment as specifying the joint distribution of how often two particular words occur in your document. Okay, and the three word is how often do three words co-occur in the document. And let's just forget about the estimation of these moments. Like, why is the method of moments nice from Pearson? Because look, it's easy to estimate these moments in data. They're just averages, right? So let's just forget about the problem of estimation. Let's just suppose we had exact moments, ignore the perturbation issue, and see if we can recover the model. And now this is interesting because we have an identifiability problem, because suppose every document had one word in it. It's very clear things are not identifiable. And this isn't even a statistical question, right? This is an identifiability question, right? And then the question is, suppose you had an infinite collection of documents and they had two words in them. Could you identify the model? What about three? And this is interesting for HMMs because unlike this topic modeling problem, we only have a small number of observations in the HMM, right? And this is sometimes referred to as the minimal realization problem for HMMs, which would be, kind of how long of windows do we need to look at before we can identify the HMM? There's an interesting question here because we expect kind of more hidden states than observations here. So it sort of seems unlikely that a short window, how big a window do we need to look at before we can pin things down? And in this parity with noise example, obviously this is the worst case because there's no finite window that'll ever work. But hopefully we're not in this bad case. Okay, so we're clear on the game. The game is now we're just going to look at the structure that arises in these moments and try to solve this inverse moments problem. And in these simpler cases, it'll be relatively straightforward. But we'll start seeing some of the difficulties, and in Rang's talk, we'll see some of the very non-trivial difficulties. So we good? Okay, just for notation, we're going to be in d dimensions. K is the number of topics or clusters. So in d dimensions, in the topic model problem, think of d as the number of words in our language. In this case, d is 4. Okay. The mixture of Gaussian one, just think of the expected value of x given it's from cluster I is mu I. This is just conditional expectation. With words, what's nice to use is what's sometimes called a hot encoding, which is represent discrete words as binary vectors where one entry is 1, which corresponds to which word occurred. So the reason for doing this is it's sometimes nice to represent multinomial distributions as vectors, right? So the multinomial distribution you can think of as a topic probability vector, right? And the reason this is nice is we can say what's the probability distribution over the first word given we're from topic I. It's just this conditional expectation, which you can write as the topic probability vector mu I. Right, so mu I is a multinomial. The entries sum to 1, and right it is. So this sort of puts them on the same footing, right? And this makes the linear algebra notation a little clearer. Okay. So we go to this. And let's just look at these models side by side. What's the first moment in our data? It's just the average vector. It's the same thing in the topic probability case. What's the distribution over words in our language? It's just the average topic probability vector.
Just to, if I understand, the sum of all mi should be 1, no?
The sum of, good, say. So let me just make this clear. Mu I is in sort of a simplex, which is d minus 1 dimensional. So this is like the probability of, say, 0.7, 0.2, which is the history. Something like this. This is basically each mu I is the distribution. We represent it as a vector. Yeah, that's right. So it's convenient. It's strange, but oftentimes with these discrete cases, people don't necessarily view them as vectors. But for these cases, it's clearly the right thing to do because we can write these moments as vectors, and then it's clear why the joint distribution of words is these topic probability vectors. There's k of them. And for the HMM, this is the distribution. So now we actually will consider the order. So the distribution of x1 is actually the distribution over the first outcome in the sequence. But these are the same. It's clearly not identifiable. Right? I give you these numbers exactly. I tell you, tell me the mu's and the w's. Clearly, it's not identifiable. So the second moment things get interesting because now we see differences in these two models. Okay, so let's look at the mixture of Gaussian model. And let's just say our noise model now is additive and spherical. So all Gaussians have the same variance. Whereas the second moment, it's just the means plus noise, but the noise is direction A specific. So we have this first component, which is, well, first part of the sum, which is how the means relate to each other. So it's sum of the mu transpose. And then we get this A specific noise in all directions due to sigma squared.
So you ignore this first order perturbation or the eta square. You know the chi-square distribution. Eta times eta is...
This is the sigma squared identity. Yeah, because each, I'm going to assume for now that... Right. Okay, good. So this is the simplest case. Rang is actually going to look at the very general case. But let's look at this. And what's interesting about this is let's just compare this to the topic model case. The distribution over two words in a document, just because they're exchangeable and they're independent, is just the sum of wi mu I transpose, because this is just as if both words were generated according to the same topic, and then we just sum over those topics. But this is really nice, right? Because once you condition on things, they're conditionally independent. And like, what's the rank of this matrix? 1k. Whereas what's the rank of this matrix? Yeah, it's D. So this is kind of nice, right? It really is a difference in these two. And this is, we start really seeing the difficulties of what goes on in these models, because once you start looking at higher moments, like each model for the most has problems in its own way of how things are getting jumbled together. But we'll try to deal with them. So now the question is, suppose I give you these exactly. Is it identifiable? I say, here's the second moment exactly. Can you tell me the mu's, w's, and sigmas? Or can you tell me these distributions? Clearly not. Well, it's clear for the mixture of Gaussians case you can. Because you just said sigma equal to 0. I'm just saying, here's a matrix. Tell me this decomposition. You can. There's no structure in it. Right. It turns out that even for this topic modeling case, the probability constraint really just doesn't buy you much. Right? You know it comes from distributions. You could constrain them to lie in the simplex. And it's not kind of a worst case theory thing. Like basically every distribution over a pair of two words is degenerate in like an uncountably infinite way. I think this was even in maybe Joseph Chang's original paper he gave. He gave one example, but we generalized it. And it's really just degenerate. But no parameter counting, things are starting to look good. Because how many numbers do we get in this second moment? It's d cross d squared. Because it's a d by d matrix specifying the joint distribution of two words.
Okay?
Okay, so you see where this is going, right? Like in the taco end. But let's, given this Gaussian mixture model problem, it's a little annoying because we have this extra stuff here. And if we're going to look at the third moment, and now you have to remember how to, do our cross terms and deal with Gaussian moments. So let's just ignore this thing because it's immediately clear what the topic model third moment looks like. Right? What does that look like? It just looks like the theory, like a very nice tensor. So now let's just do some definitions. A second moment, let's just define it to be M2, which looks like this. The third moment, because all the words are generated independently, it again just looks like the average as if the three words were generated according to the same topic. So it's the sum of wi, mu I, mu I, mu I. Okay. So now, right, we can just forget about, is this clear? So now let's just forget about the particular statistical model and just think about this as a math problem, right? This is a problem. I give you a matrix. I guarantee you it has this structure. I give you a tensor, which is d by d by d. I guarantee you it has this structure. And I ask you, can you tell me the mu's? Is it identifiable? If you can show me it's identifiable, then we've at least answered the question that documents need to be of length 3 for us to identify the topics under this very simple model. I mean, this is the simplest case, but it's nice. Like we can pin it down. And of course, this is the stuff people in the room here are experts on, which is tensor decompositions, right? And now we're considering this case where the number of topics is less than the number of words in the language. Okay? So sometimes in statistics we refer to this, and computer science we refer to this as the undercomplete case, but this is pretty reasonable here. What this allows you to do is it allows you to make these topics orthogonal. And so anytime you have a matrix that's low rank, it's nice to whiten the matrix. So do a linear transformation of the data that make it look like the identity. Okay, so we're just changing the coordinate system, and this effectively changes, kind of projects everything to a k-dimensional space. Because basically we know the range of the topics, and so we make this look like the identity. This transformation allows us to work in a k-dimensional space. It's also nice in that it makes these topics orthogonal to each other. Okay, so basically just do this transformation, it's linear, and now we have an even nicer reduction, which is, I say, here's a tensor, it's of size k cubed, I guarantee you this decomposition exists, and these mu's are orthogonal. And if you can find it, you can just undo your linear transformation. This is an orthogonal tensor decomposition.
So you're saying you use the M2 and diagonalize it and use that transformation on M3?
Exactly. Yeah. Right, this is sort of the right way. The earlier results, so HMMs were confusing because it was an asymmetric tensor, and somehow the community that understood them didn't quite understand the connection, and they were doing simultaneous diagonalization tricks, and we kind of, it took people a while to realize this really was a tensor decomposition because you had this mysterious simultaneous diagonalization problem. Because someone in HMM, this really is asymmetric because your tensors are arising from the joint distribution over 3 outcomes in a row.
Just this is the certainty of identity because it means that k is equal somehow to d.
No, it's k is less than d. So
how you are going to get the identity matrix?
You just
so you just throw away the small numbers. So you're just projecting the topics down to a d-dimensional to a k-dimensional space.
So you're going to cut the dimension.
Yeah, and this is actually good in practice because in practice, you never want to explicitly write down a dense distribution over 3 words in the language. I mean, technically this is sparse, but it's a horribly large tensor.
Dimension in such a way that you have it. Okay.
Yeah, that's right. That's right. So this is actually practically pretty nice in the empirical setting where you don't ever want to explicitly work. You have to be careful about working with a d-cube size object in certain problems because d is very big. It's sparse, but it's still big. So this cuts down the dimension. And basically this is just the sort of the nicest generalization of the SVD because if I didn't have this is an SVD. Right? And if I do have this, then we just inherit the nice properties of orthogonal tensor decompositions. And the way we define eigenvectors, we can define that for tensor 2, which is an eigenvector of matrix, is you hit the matrix by a vector, you get a vector. I'm just defining kind of notation here that this multilinear notation is a tensor has a few indices. If you hit it with vectors, you just kind of sum out the tensor with each vector, summing over the indices, just like we do for matrices. The tensor eigenvector, you can define it the same way. And there's been numerous people who have done work on orthogonal tensor decompositions, like Tong Zhang and like different communities. So we basically know that these things exist. We know they exist. Basically, what do we need for this thing to work out? We just need these mu's to be linearly independent. And that's sort of what breaks these hard cases. It's sort of a non-degenerate property. So this is really the proof in the exact case. We just find the eigenvectors of this tensor because it's orthogonal. They satisfy this property, right? And what are the solutions to this equation? The v's have to line up with the mu's, right? This is the thing we know. And these are exactly the topics. This is classic estimation problem in statistics. Well, you have this exactly, that the tensor eigenvectors are the topics in the language. You just have to unwhiten them. Kind of neat. And it also hits the identifiability question, because now, at least for the single topic model, we need to know the documents are of length 3, and that suffices. Something's clearly going to break in this HMM case, because we needed this k to be less than d. There's no way you can get k linearly independent vectors if k is bigger than d. So something's going to break there. But this is the right intuition, and the theorem is pretty clear. As long as these mu's are linearly independent, the eigenvectors of this tensor are in fact the topics. I call it robust just because of the saddle point issue. That's a minor issue. And then, and why is this okay? Well, in general, tensors are horrible, right? For arbitrary tensors, there's not much we know about existence of decompositions, any estimation in them. Typically, there's just hardness results. Why are things okay here? Well, I've posited the structure of the tensor is coming from a statistical model. That's why this is okay.
It's a quadratic problem now. It's the eigenvalue problem.
Yeah.
Not the standard one. So we know that in general it's NP hard, but this one you claim you have to convince me that this is easy, right?
Yeah. No, but you can solve this with, so a different way to solve this is you can actually solve this with 2 SVDs. Basically you can actually, if it's exact, one way to solve this is actually doing 2 singular value decompositions. We can do it with an eigen.
You unfold it, and then you do SVD on one, and then you claim that it's going to be, you already identified.
Yeah, that's right. In the exact case, there are many ways to prove this. And
generically, you're right.
Yeah, but what I'm saying, the interesting case now is now we can go to Moses' question. If we actually want to do this in a reasonable way with finite samples, like the first time we tried this, like in practice, this is when it became clear, from our community, like, look, this is clearly more structure in it because these simultaneous diagonalization methods, they're kind of a bit of a disaster in practice because you're taking random slices, and this power method is much more stable. But to really address the statistical complexity question, and this part was interesting because we have to understand what happens with a perturbed tensor. We know roughly what the algorithm is going to be if we try this eigenvector thing, but we have to go through the details to see how much error we can tolerate. And this is like the analogs of these matrix perturbation results, like Davis-Gahan-Whedon's theorem. But those are very nice for matrices, because what do you do in the matrix land? You just take your perturbed matrix, do an SVD on that, it exists, and then talk about how close the SVD on your perturbed matrix is to the original. You can't do this in the tensor case, because once you have a perturbed tensor, you can't just say, do the tensor decomposition on this tensor, because it might not, like, there are many different methods, it's not guaranteed to exist. So we need an algorithm, and now this comes the kind of hairy analysis part, which is, what is the way we can, not in the limit, with a quantifiable perturbation and a quantifiable algorithm, what can we say about a perturbation result in this undercomplete setting? As far as I know, the result we have is basically the sharpest you could hope for. So I don't have the details here. But basically do I have them? Okay. So basically the idea is you're going to run a power method on this, okay, and use the results of a power method, and we're going to do a perturbation analysis. But this is tricky because of the perturbation, you aren't guaranteed the power method will converge. Because basically if you start near a saddle point, the error ball around it, we don't know how to guarantee that you'll leave. So there's got to be some condition as to how small the initial error is so you can escape. And then once you escape that, there's a question of, do these things really compound? And basically show here, and to some extent, we needed this just to do the sample complexity result, but it's really an analog of Whedon's theorem. But what's interesting in the tensor case, in Whedon's theorem, what really matters are eigengaps and Davis-Gahan between subspaces, because that's when degeneracies occur. But in the tensor case, there's no degeneracies, right? You can have, like in this theorem, you can have WIs that are repeated, but it doesn't cause you any problems because each one is stable because of this power of 2. So somehow what's going to characterize the stability of this problem can't be an eigengap. So the analog of kind of Davis-Gahan for tensors is actually how large the eigenvalue is, not the gap. Okay, so then basically formally, the way we prove this for a generic perturbed orthogonal tensor is the analog of Davis-Gahan, but we quantify with high probability how many restarts one needs, how big the error region needs to be, because we really want a polytime result here. And there's definitely a slop here in that the initial error we need, we think could be smaller, but the problem is you have to sort of with high probability, you want to say you're going to start in a reasonable place where the tensor power iteration works. But at any rate, the short answer is we can do analogs of Davis-Gahan for the tensor case. It's algorithmic dependent. That's important to really doing the statistical analysis because that's in the paper. But now it's just how accurate do we estimate these moments with data? What does that translate into parameter estimation? And as far as we can tell, I think the best generic way to do this is through this orthogonal tensor decomposition and this perturbation result. As far as I know, we haven't seen it, and it takes a lot of work with randomization to get it right.
So in this method, what you do essentially, you're trying to find the maximum eigenvalue singular value, right? Your tensor is symmetric, I think, right? Mm-hmm. Your tensor is symmetric.
We want to find all of them, not the maximum.
That's right. But then you see, these tensors, the maximum one is the one, but what, so because you take argument of maximums that you're trying to find the maximum one.
You're right, but the point is, the thing about these tensors is in the matrix problem, only the maximum you'll find, sort of generically. In the tensor one, everyone is stable. So what's interesting about these tensors is we actually want to find all local maxima. So there's no guarantee we'll actually find the max.
not local maximum. For my eigenvalues algorithm, it's just a critical point.
Yeah, that's exactly the point. The critical points are unstable, and this is exactly the restarts we need, because if you start too close to a critical point, you could bounce around, and we don't know how to prove things. So the actual proof explicitly shows that with high probability, you will not get to a critical point. And basically, what happens in the perturbation analog of a critical point is if you're at a saddle point, we just don't know if you'll converge. So we explicitly, and sort of what governs the difficulty of this problem is the smallest eigenvalue of some topic. So we do actually explicitly characterize this.
So the first one you do it with maximum, then what's next?
Oh, no, right, so that's the point. We do the first one, we might not even find the maximum, but we are with high probability guaranteed to find one of them. Okay. Then you deflate, you take that out. It turns out you don't even need to deflate, you just keep randomizing, you'll find them all.
Tensors very cheap.
That's right, and this is like this is exactly the difficulty of the proof, is actually showing this for the orthogonal tensor decomposition. Like in a sense, this theorem we did was just an abstract one that had nothing to do with the statistical problem. It was just a tool we needed to do the statistical efficiency analysis and the finite computational analysis. But it's clear, at least in some settings, we might have structure for improvements. But I think in the generic case, if we wanted to have a polytime algorithm, I think this is the sharpest thing we can tolerate. So, yep. The algorithms for the independent component analysis? Yeah, so basically, these decompositions arose in many different areas of computer science, statistics, and so on. And some of the ICA community, they knew their model really had the same algebraic structure when you did different manipulations, but somehow this connection wasn't made to all the other latent variable models, which was very strange, and it was like 20 years later. But this was sort of rediscovered in computer science, and these crypto results that there's some like Oded, yeah, Oded, right, yeah. This is again, he rediscovered this as well because he broke that crypto scheme showing that you could solve this problem. And so definitely this community has studied these algorithms a lot. They're kind of questions of interest were a little different, so they didn't really study the sample complexity issues directly, but not surprising, this is a good idea. It's kind of been discovered in many communities. Yep.
The speed of convergence?
So yeah, basically, if you get close, these things are quadratic because you've got this this power 2. Sorry. It's super fast. It's much faster than the matrix power method in this case because you have this power 2, you get quadratic convergence. Yeah, so this is in the paper, but it's very clear that in the exact case it's crazy fast. But the gap depends on where you start. It's sort of which thing do you overlap the most, but it kills it.
Well, maybe it's quadratical to try the first one, but then there are many. No,
it's always quadratic based on the overlap between whichever eigenvector and sort of your starting point x. Like that's sort of what. It's always quadratic. But the sort of rate of, like in the eigenvector method, it depends on some coefficient. Here, it depends on the starting point because.
But I am confused because the eigenvectors can be more than k, because this is a 3-dimensional tensor.
Yeah, I'm assuming that there's only k in there. That's the key of this.
I mean, these are not general things. These are things that up to orthogonal transformation look like alpha 1 x
that's right.
plus alpha n xn to the d. These are very non-general things.
Yeah, and that's exactly why we can solve this, because these statistical models give rise to very specific tensors. And in a sense, you're right. For the HMM case, k is bigger than d. So you can't orthogonalize. Okay? So yep, one more.
So do you get similar kinds of bounds even if you consider take into account the whitening step?
Yeah, basically this just, in a sense, whatever whitening you do, like this doesn't say it statistically, this is just saying you have a t plus an error tensor, and you make some spectral norm bound on the error tensor. So it's easy to just say, look, if I have whitening error, just push that into the error tensor. And it's interesting sort of which problems where the error dominates. Is it the whitening step or the, like in sort of community detection, this is Yeah, this is a lot of delicate issues because, and if you have tricks to start closer to some answer, you can push this original error ball down. So Rang played this game for community detection. So this is.
I just wanted to make sure I understood what you're saying. Is that so you can actually put down a grid of start points, run them all in parallel on different processors, and find all the eigenvectors. You don't have to deflate. You don't have to.
Yes, but that's exponential time. The problem is that's exponential in the dimension.
You can find them all separately. You don't have to.
Yeah, that's right. That's right. That's right. That's right. So you don't want to do a grid because that's exponential time. And it is exactly the sample complexity issue for resampling. A different way you could do the proof is actually just keep randomly restarting and do it. But this is the key, that in these high dimensional things, the grid is the devastating. Like if you do that, like we didn't need the tensors to begin with. I could just sort of search the space for the mu's directly. And so let me definitely take some more questions. But if we're good with this one, I would like to back up to this mixture of Gaussians problem. I kind of swept that under the rug because this is a super nice case, but this is clearly a tricky problem. This breaks.
It's because you see if your perturbation is small, then easily you identify the low rank which is close. And then
Yes, but that's right. So if the perturbation is small, sure, we can throw this away. But that's not the case we want to solve. We would like to solve the general case. Because think of this problem. This is degenerate, but sometimes we're actually interested in cases where our clusters overlap. And statistically, like if we didn't have to worry about computation, statistically there's no problem identifying this problem. So we do want to solve this problem, and there are definitely interesting cases where we don't have these massively separated Gaussian. So certainly we could ignore the sigma by just appealing to perturbation, but we want to solve the problem, the statistics problem. Okay, so how do we do that? So I give you this. What are you going to tell me? So can you tell me sigma?
if you take the if sigma is small.
No, it's not saying it's not small, but it's getting close. What's sigma? If I give you this matrix exactly, I tell you it has this structure. Can you tell me sigma?
K is small enough.
Yeah, it's the minimal eigenvalue.
Yeah, so then it's one of the eigenvalues.
Yeah, it's the middle one, and that's the point, because somehow in high dimensions, you're always going to have sigma direction in a direction orthogonal to the means, right? Because you basically in all the directions you have at least sigma variance. So the means live in some subspace, so you can just rip sigma out and subtract it out. And now if you just look at the third moment, what happens? Well, the third moment in this problem basically just mixes up some sigmas in there. Like what is the third moment of a scalar Gaussian? It's like the mean plus 3 mu sigma squared. Right? And that's the point here. We can estimate sigma. This third order moment is just jumbling up some lower order moments. So you can just subtract it and basically you can play the same game. So take the second moment, take the minimal eigenvalue, subtract it out. That makes a piece that we want. And think of this mess as just 3 times the variance times the mean. And I'm just kind of swapping things around to make it work out in the tensor way. But by doing this, I create moments that look exactly like the problem we can solve. Because I'm kind of, yes, this model screws up the higher moments, but we can look at the structure in these moments and take it out. None of this is heavily relying on the spherical noise property. This particular technique, we can do the differing sigma I case. But the more general case is these are PSD matrices. And this is like now your tensors are made up of PSD matrices. And that's what Rang will talk about later. But the simplest case is giving us the idea of what the game here is. If we really wanted to play this inverse moments game, sometimes there's tricks we can play that can relate it to a tensor we care about. And that's all there is to this. This is basically the proof. And then it's the sample size issues are, again, just perturbation arguments. And with respect to your point, when sigma is small, yes, you're going to need more samples to estimate it, but you can still do it. And you would expect that, because as sigma starts becoming large, you expect the problem to become more difficult. So the sample size is going to grow, but one can quantify that. And it behaves like nicely. It's not like exponential on sigma. And somehow these bad cases are basically degenerate ones. But there's some interesting bad cases like HMM. Like, like HMMs. Like we do care about this case, because sometimes we do want to model processes that are low dimensional and have many hidden states. And just to end on this, what's the thing one would try if you had this process? Well, if the topic model is degenerate, what you would like to do is sort of group words together and call them a word. I would like to look at a 6 tensor and say, well, it's really a tensor made out of the first 2 words, I call them a word, and the second 2, and the third, something like this. So I want to make tensors off of groups of things together. Okay? So certainly this gives me more parameters, and definitely things are becoming exponential here. So that's bad, but the point is, we have a lot of parameters to estimate, because suppose if we've got k states here, there's a k by k transition matrix here that we need to estimate. So some amount is reasonable. And this window size for HMM is sort of how big do we need to make these windows for this to work out. Now the topic model case, it's sort of easy to see that something like this will work. The problem here is once you start blowing up these window sizes, is that you're also blowing up the kind of number of hidden states here. So there's this interplay. Like if it was the identity matrix, then this is an easy problem, because I could tack these together and the hidden state here is just the same. It's only one of k things. But in this HMM problem, once you start looking at larger windows, this kind of nice structure goes away once you look at it still is some structure, but it's a bit different, because somehow what you want to call the hidden state is growing like also exponential in your window size. So you have to be a little careful about this. It turns out, this one we posted a recent paper, basically arguing, the parameter counting is about right. So if your window is bigger than sort of log d of k, that's the size of the windows you need to consider. So that's sort of the length of the moments you need to use to estimate the model. Now there's subtleties, because there's this classic problem in EE called the quasi-realization problem, where you can represent HMMs as automata in different ways, and that's how we do it here. And then there's games to actually learn it sort of in the model. But the basic point is, once things become over-complete, where k is less than d, sometimes the game actually changes in subtle ways, and that's what happens in this HMM problem, because you have to play a few games. But the high-level point I'm trying to emphasize is just that what's the game? Try to look at the structure in these models. Sometimes they are related to things we can solve, and they're related to things we can solve in ways that we can both make computational and statistical efficiency statements, both kind of quantify the sample size we need, the runtime of our algorithm, and understand what properties of the problem govern the difficulty, things like minimal eigenvalues and so on.
So are you really saying generically, or you mean if you have some distance function?
So this is good. So it's not so this one is not technically a smooth analysis model. So it's just with exact moments, if you just perturb it and had exact moments, then you could solve the problem with this.
But do you have bounds on the?
We don't have strong bounds on the perturbation, and Rang and Xing thought about it, and it's delicate. Now the Gaussian mixture one we do, but somehow it's subtle getting that. I mean, this is the right question, but it's subtle getting that here, because somehow, like even the proof that it's generic, like basically the proof that it's generic is difficult, let alone.
So how does this compare to the results of Coleman Matthias works? What do they prove relative to this?
So they give identifiability claims, but they don't have generic claims on window sizes. So this is like, in some sense, this is right because it says parameter counting is OK. But it clearly breaks for the parity noise problem. It also is not smooth analysis, which is what you would really like. And I think it uses some delicate, I don't know, you could like some Gush-Cohen. So there's some delicate way of bounding eigenvalues away from 0 for this problem. OK, so Yeah, and if you've heard of LDA, there's like this topic model where you could have many different things. The same idea kind of goes through. So the short summary is these ideas are coming up in machine learning and statistics because we have structure in our models. Sometimes it's reasonable to posit the structure is reasonable, and if, as opposed to worst case, like if we believe the model, we should look at the structure in the problem. And these inverse movement methods do seem to allow us some reasonable way to get at parameter estimation in these problems, where we can think about computational difficulty, statistical difficulty, and they seem to be giving to some reasonable algorithms because basically, they're just trying to find directions which your data is very skewed, and that's nice. Like just even as a heuristic, this seems like a reasonable thing to do. In terms of collaborators, Daniel and Nima have been working on this for quite some time. All of the tensor stuff, Rang and I have been working on, and Ching Ching was an intern this summer, and she did some really nice work with us on this HMM problem and the Gaussian mixture problem that Rang's going to talk about later. So, thanks.
Are there any questions for Sham?
May I know, in the case when you have dimension B and rank K, in the practice, what could be the value of K and B for the documents topic case, for example?
Like at some level, the problem is these models are always wrong in practice. So the question is, are these abstractions a reasonable way to estimate the problems? I would say for topics, like hundreds to thousands are reasonable. Like looking at like hundreds to thousands. Hundreds to thousands? Topics. No, topics. So words that you have like, so it's right. So D, D, it's the number of words in the language. So typically, if you use Wikipedia, you're looking at 10 to the 4 to 10 to the 5, 10,000 to 100,000 words. And K, you would like your algorithm to at least get 100 reasonable topics, but you should be able to get, you'd hope to get more. There's a question of interpretability of these things, which is an interesting question, but, from my perspective, I'm interested in using these methods, not so adamant that I really care about topics, but as like features to interesting problems. And then like give me as many as I can. Yeah, like the more features I get, the better. For any problems.
Do you know your collaborators have any question that an algebraist or algebraic geometer might be able to answer? How can we contribute to this endeavor?
Well, robustness is a big question here. So, and this is sort of hitting the limits where we don't know what's happening because, there's sort of in terms of my very crude summary of the problems we solve in this area, we either assume very strong modeling properties, which gives rise to the structure, or we assume like incoherence, where these tensors are very orthogonal, and then you can pull out like many, many more out of there. So somehow, is there a way to think about it's a wide open area, but it's sort of, is there a reasonable way to think about something in between? Because, so I think robustness is one of the biggest ones. There's sort of the question on our side is, are these reasonable abstractions to the world, which I don't know. Like maybe these things don't work on a lot of problems, but if that's the case, why are we using these statistical models anyway? It is kind of a question in my mind. So, because these aren't anything fancy, right? They're saying, look, these are the correlations we expect to arise in practice under the model. If we can't capture them in this model well, then what are we doing in the first place? Like maybe we should be thinking about the problem very differently. But I would say robustness is one of them.
Finding some good starting point. I guess I would phrase it as quantifying genericness in some ways.
So this is right. So quantifying genericness is this is a nice way to put it. And I think a lot of the talks today are going to be discussing that because these are all the easy cases we've looked at, and the HMM is a bit harder because any time we're in the overcomplete case, it's tricky. And you guys probably know about this like Foubi result by the de la Tower. There's a result when K is like D choose 2 in generic, you can decompose one of these tensors exactly. This is a really beautiful result by de la Tower and others. And
that's Grushko's result.
No, they're computational.
Yeah. You mentioned this example with words and topics.
Mm-hmm.
And you said if you have like 10 to 12 full words of 10
Yeah.
But then if you take a triple tensor of that, wouldn't be the size? Is the size still manageable or?
Yeah. So the point is the number, it's sparse. So the number of things you're going to have, the number of entries is going to be no more than the length of Wikipedia because. Right. Okay, if you do exchangeable, then it's a bit more, but it's still super sparse. Like if you just did it in the HMM case, it's never going to grow past that size. So you can definitely manipulate these things as sparse objects, but this is why like in practice, the whitening step seems to be better because you can actually take the tensor, make it a k cube size object. 1,000 cubed is fine. And at that point, what seems to be actually better in practice is to actually use like alternating least squares. Like start reasonably, and that really works well. It's fast. But yeah, so managing, sparse is like nothing particularly deep there for the answer. But it's interesting that the time it takes to manipulate these things typically is just the construction of the tensor and the projection. The actual power method or whatever you're doing, or the alternating least squares, like it's super fast. It's literally just reading your data, constructing this object, whitening, and so.
Okay, there are no more questions. Let's thank Sham again. And we come back at 10:20.
As Shakespeare.